Hello viewers, welcome back to my channel. We're still moving on with our topic of dim lenses. Now in the last lesson we looked at the eye and the camera. Okay, we saw that they both have a screen, they both have a lens and all that stuff. We even compared we looked at the comparisons between the eye and the lens and the camera, and we also looked at the differences between the eye and the camera. So that is in my last video. If you're not conversant with that, go back and check and you'll be okay. So today we are going to look at something different. We are still under applications of lenses. Don't forget, we are still under applications of lenses. So today we are going to look at what we call eye defects. So we're going to look at the defects of the eye. We're going to look at the defects of the eye. Now, we're going to look at two main defects, okay? Two main defects that can be corrected using our biconcave and biconvex lenses. One defect is what we call short-sightedness. The other name is myopia. So we have what we call short-sightedness. The other name is myopia. Okay, so that is one of the defects of the eye. So what causes this defect? Now, if we draw the eye again, the normal eye. Now, of course, I'm not going to draw the diagram like I drew in the last lesson. We are drawing a simplified version of the eye. It's more of a ball. Let's say that is an eye with no defect. Let's say that's my eye. An eye with no defect. Okay? This is the cornea, the front of the eye. We said most of the refraction of light takes place at the cornea. And then, of course, we have our lens, which is suspended by the ligaments, which are also connected to the ciliary muscles. So we don't go back to that. Okay, that's our lens. Now let's say this is the eye of, I don't want to say a normal person, an eye of a person with no defect, an eye with no defect. Let's say that is a normal that eye. Now, the eye of a person who is short-sighted is this eyeball is a bit longer. So I'm going to dot this region. Okay, because that is not the actual so that should be the correct position of the retina for an eye with no defect. This should be the correct position of the retina for an eye with no defect. But for an eye which is for an eye that is short-sighted, the eyeball is longer. So instead of the distance being from the cornea to this point, then it is from the cornea to that point. So this person is short-sighted, courtesy of the eyeball being longer than the eyeball of an eye which has no defect. Okay? Now, let's see what happens to rays that are coming from an object. Now, for rays that are coming from an object that is near. Let's say this is an object that is near. The rays come from the object. Of course, there will be refraction by the cornea before we get to the eye. Okay, so those rays that are coming from the near object is the object which is near. Just write, let me write capital N. That's an object that is near. Those rays come and they converge where we have the retina. Okay, they converge at the rightful place where we have the retina. But for those rays that are coming from a distant object, confusion. For rays that are coming from a distant object, those rays are not able to converge where we have the retina, but instead they converge where they would converge where the retina of a normal eye is supposed to be. So our actual retina is here, but they converge on the false retina. Okay? And the false retina is in front of the actual retina. So rays that are coming from far object converge in front of the retina. Why? Because that is where we have the false retina. That is where the retina should be. But it's not there, it's behind. Because the eyeball is a bit longer. So when we have that condition, then this person is able to observe objects that are near. These are rays coming from the near object, but is not able to observe rays that are coming from far objects. So when that happens, then the far objects, this person will not be able to accommodate, but they will be able to accommodate objects that are close to the eye. That problem is called short-sightedness. And we have said one of the cause is a longer eyeball. Okay, a longer eyeball. So cause, one is a long. Now the other problem, the other problem could be the eyeball is the correct size. Yeah, is correct size, meaning the eyeball of this person who is short-sighted is the same as the eyeball for a person with no defect, but the lens is the problem. Now this lens could be a very strong lens which has a very short focal point. Okay, a very short focal length. Now when the focal length is short, it means this lens is it is refracting rays so much that the refracted rays converge in front of the retina. So either way, the person will not be able to observe those objects that are far. So the other problem could be a lens of shorter focal length. An object, a lens with a shorter focal length. So it could be a longer eyeball, or it could be a lens of a shorter focal length which converges these rays so much that they converge in front of the retina. So the question is, how do we resolve this problem of a longer eyeball of a person who is short-sighted? We resolve that problem using glasses. That's the cornea. That is the lens. And that is the retina, of course. This is that should be the rightful place of the retina, but it is behind because the eyeball is longer. Now these rays that are coming from a far object, we put a diverging lens. Let's say we put a diverging lens there. Okay. So what would happen? This is a diverging lens, so we expect that the rays will be diverged. They will be diverged. So we have some diversion, or the divergence of the lens. We draw this. These are rays coming from a far object, and after getting to the lens, they will be diverged. Okay, so you can see the divergence by the lens. So they came parallel. Remember, we are like talking about rays from infinity. They come from parallel, from very far. Of course, to our lens, it is infinity because the distance is far. So they come parallel to each other. So when they get there, then they are converged. They are diverged. So when they are diverged like that, then now they can move because there will be refraction. Now they can meet. Drawing is becoming hectic. Okay. Now they converge at the retina. Okay. Now, when you look at those rays, if you produce, this is the ray after divergence by the biconvex, biconcave, I'm sorry, biconcave lens. If you look at this ray, where do these rays look like they are coming from? Okay, they don't look like they are coming parallel from a far object. If you produce this ray backwards, when you produce this ray backwards, the object looks like it is there. And this object is a virtue object. Let me put it dotted. So let me do it again. This is the ray after refraction. So the object is virtue. Why am I saying the object is virtue? The rays look like they are coming from this point here towards they look like they are coming from this object here towards the cornea. But the reality is they are not coming from here, they are coming from this direction. So it's like you have brought the object closer to the eye. It's like you have brought the object closer to the eye, you have moved it from very far, and you have brought it closer to the eye. That object is a virtue object. Of course, it's not the real object. It's a virtue object, and it is forming. It's on the same side as the diverging lens. So once you've done that, now the rays now can fall on the retina, because the rays that were so close have been diverged by the diverging lens. So they fall on the retina now at the right place, and now they can fall on the retina. Now when you look at this diagram and this diagram, you could see some similarities. Okay, you could see some similarities. Now when you look at these rays, these are rays that are coming from the distance object. Normally, before they were able to, they went to the retina, which is false, where it should be, but it's not. And now we have put, and these rays are coming from a near object. Those ones reach the retina. Now, when you compare this diagram and this diagram, what are the similarities? After using the diverging lens, the rays now have been diverged in such a way that they look like they are coming from where the original object is, the near object is. So this object and this object are near the lens, where this is the actual object, which is an object which is closer to the eye. But this object here is a virtual object, is a far object that has been brought close. But it has been brought close to look like it is the same distance as a near object. So that is a diagram. We have used a biconcave lens, a diverging lens. Okay, so let's look at the other problem that we have. Is called long sightedness. Or we call it hypermetropia. Now, I don't want to delete those diagrams. Now, in this case, the eyeball is shorter than the eyeball of an eye which has no defect. So remember, this one is longer, so this one is going to be shorter. So if we draw the eye, we draw a shorter eyeball. Okay? While for a person with no defect, it should be there. If this person did have a defect, probably their eyeball should be behind there. But for this person, it is shorter. So what happens? What happens is this person is able to focus those objects that are coming from far. Oh, forgot to draw a lens. Okay, so those rays that are coming from far, they come. And they come and they are diverged to meet on the retina. So these rays are coming from far. Say they are coming parallel to each other because it's like they're coming from infinity. So those rays are able to form on the retina, which is much closer to the lens because the eyeball is short. Okay, what about an object that is near? What about the object that is near? So these rays come. They come like that. And how do they converge? Because remember, they are going like this, they are like diverging rays. They are not like they are diverging rays. So they converge behind the retina. Focusing them is not a joke. So these are rays from an object that is far. This ray is coming from a far object. It converges at the rightful place where we have the retina. But the one that is coming from a near object, that one converges behind the retina where the actual retina should be, but is not. So this problem here, why has it occurred? Why are the near objects not able to be accommodated on the retina? Is because the retina is very close to the lens. So those objects that are near, their images fall behind the retina. And when their image falls behind the retina, then we cannot be able to see them. So now the question is, how do we resolve this problem? A problem where all far objects can be accommodated, but near objects cannot be accommodated. Then we are going to use a different type of lens. So I'm going to draw the eye again. Okay. This is the far point where the retina should be, but is not. Then we have the cornea. We have our lens. Okay. So these rays that are coming from near, so this, if I have a near object here, these rays that are coming from a near object, I can put a converging lens closer to the eye. Okay? For what? Let's see. A converging lens converges the rays. The rays were diverging like that when they were coming from the object, and then it converges them a little bit. So before they get to the cornea, they'll be a little bit converged. Okay? They've been converged a bit by the converging lens. Now, once that has happened, now they can be able to focus. So we can be able to focus correctly on the retina. So before they went behind, they converged behind the retina, but after using a converging lens biconvex, these rays are converged before they come to the eye. Before they meet the cornea, they are a little bit converged by the converging lens. And once they have been converged like that, now after being converged by the cornea and by the eye lens, now they can meet on the rightful place, the retina. Okay, so those are the two defects that we have, the two main defects that we want to look at today. So what is the cause of this? So one, we have talked about a short eyeball. The eyeball is shorter than the one of a person without defect. It is shorter. Okay. The other problem is the lens itself. Previously, we said the lens had very short focal length, meaning that now it converges light a lot, so that now images were forming in front of the retina. This time it's the opposite. The focal length of our eye lens is too long. The focal length of our eye lens is too long, so that now after converging, the images are forming very far from the lens. So a longer focal length, remember, if you can even imagine the rays coming from one point and a shorter focal length and a longer focal length, of course the one that is long will form images far than the one that is short. That's why you are seeing when the focal length is short, images form before we get to the retina. But when the focal length is long, then images form far from the lens and they might form beyond the retina, which now gives us the long-sightedness. So this one is a lens of long or longer focal length. So we have looked at the two defects. One is short-sightedness and the other one is long-sightedness, and we have seen the problem is either with the size of the eyeball. It could be longer or shorter than that of a person with no defect, or the problem could be with the eye lens. Okay, the problem could be with the eye lens. Either the eye lens has a very short focal length or the lens has a very long focal length compared to the focal length of an eye which has no defect. So either way, whether the focal length is long or short, or the eyeball is longer or shorter, we are going to have these defects as long as we step out of that region of an ordinary eye with no defect. Okay, so that brings us to the end of our lesson. I hope you enjoyed the lesson. Now you know how to correct short-sightedness and long-sightedness, what type of lens to use. Don't forget to share and subscribe. Also, don't forget to like. When you share with people you think will benefit from these lessons. I hope to see you in my next video. Until then, goodbye.